Thank you everyone for checking out this talk. This is Joy work with Badih, Ghazi, Ravi, Kumar, and Jelani Nielsen. We studied several problems relating to counting elements in time windows, and they share the following common structure. There are n items from 1 to n. Each item I is associated with some input xi, which we will discuss in a moment. Given these xi's, we would like our algorithm to compute an estimate of some query q. Now there is also a time horizon parameter t, and in the most basic count distinct problem, each xi is a Boolean vector of length t, where the jth coordinate denotes whether item I occurs at time j. For example, if t is equals to 5, then this may be our input. Now the query that we want to answer has two parameters, s and f, the starting time and the finishing time. And what we want is the number of items that occur between time s and j. For example, here if we want s equals to 2 and f equals to 3, then it means that we want to count all the items that occur in time steps 2 or 3. In this case, the item x1 is counted because it occurs at time 2. The item 2 is not counted because it doesn't occur in either time step, and the item n is counted because it occurs in both time steps. So if there are only these three elements, then the answer to this query would be 2. Now we also consider a more general problem, which we call k occurring elements. The setting is similar to before, except that each vector xi is now not just a Boolean vector, but each coordinate can be an arbitrary integer. And the jth coordinate of xi now denotes the number of time that item I occurs at time j. For example, again, this may be our input. And now the query that we want also has an additional parameter k, and we want to count the number of items that occur at least k times within the time step from s to f. When k is equals to 1, this is equivalent to the easier count distinct problem that we already discussed. Just to give you an example, let's say we have k equals to 3 here, and s equals to 2 and f equals to 3. Then again, we want to look at these two time steps. But now x1 and x2 occurs only twice in these two time steps combined, so they are not counted in the final query answer, whereas the last element occur exactly 3 times, so it is counted in the final answer. So if there are only these 3 elements, then the final answer should be 1. So those are the type of queries that we are interested in. But we also want to answer this query while preserving the dataset's privacy. And we are using the notion of differential privacy. Roughly speaking, differential privacy says that if we take a look at the output of the algorithm for two neighboring datasets, x and x prime, then the output distribution should be similar. And this similarity is parameterized by two parameters, epsilon and delta. For those of you who haven't seen differential privacy before, epsilon is the multiplicative approximation, whereas delta is the additive term. And epsilon should be thought of as a small constant, whereas delta should be negligible in the dataset size. In our setting, we would like to not just answer a single query, but we want to answer a family of queries. And we want these answers to simultaneously be differentially private. There are three families of queries that we consider in this work. The first is cumulative queries. These are the set of queries whose window begin at the very beginning time step. In other words, we fix the starting time s to be 1 and let the finishing time f be arbitrary. In this example where t is equals to 5, there would then be 5 cumulative queries. Next, we consider the fixed window queries. In this setting, there will be a fixed window size W given beforehand, and we only consider the windows that are exactly of size W. In particular, in this example, we would have 3 queries if the window size W is equal to 3. Finally, we consider the family of all possible queries without any restriction. So we consider all possible S and F. So in this setting, there would be T choose 2 queries. So we have specified the queries that we want, but one additional thing that we haven't specified is the notion of neighboring. In differential privacy, neighboring relationship governs how strict the privacy constraint is. Recall that we require that the output of any 2 neighboring datasets be similar. So if we set the neighboring dataset to be more general, then this constraint is more stringent. It is harder to satisfy, which means that it gives more privacy protection, but it will be harder to design an algorithm for. In this work, we consider 2 neighboring notions. The first one is the so-called item level setting. This means that we can make an arbitrary changes to a single item. For example, in these 2 datasets, x and x prime shown here, we change x2 to x2 prime, where there are changes in many coordinates. This is in contrast to the second neighboring dataset, which is more restrictive, where we only allow a change in a single occurrence. In other words, we only allow an addition or subtraction in only a single coordinate of a single item. An example is shown here where x2 and x2 prime now differs on a single coordinate by just 1. Okay, so those are all the possible settings. One last thing we have to discuss is the accuracy notion. Recall that differential privacy only allows for randomized algorithm, so we cannot hope to be correct 100% of the time. And we have to define a certain notion of utility or error so that we can discuss the accuracy. In this work, we say that our algorithm achieves an error E if the expected error of each query is at most E. Now, there are also other notions of errors that have been used in literature, and our results, as we will see in a moment, also apply as well, but there will be some change in the polylogarithmic factors. So we are fixing this notion for simplicity and also for consistency with previous work. All right, so with all of those in mind, we can now state our result. For simplicity of the presentations, we will only focus on the PLDP setting where delta is equal to 0, and we will assume certain parameter regimes such as the epsilon being constant. So the errors that one can get depends on the notion of neighboring in DP and also the type of families of queries. So let us start with the event level DP setting. In this case, the cumulative setting was actually already studied before by Bolot et al., who gave an algorithm with error log to the 1.5 t. They also asked whether it's possible to get a polylogarithmic error in the fixed window setting. And we answer the question by showing that there is an algorithm with error k times log to the 1.5 w, and recall again that w is the window size here. Interestingly, the cumulative setting, there is no dependency on k at all on the error, whereas in the fixed window setting, there is this multiplicative k factor. So one might wonder whether this is necessary. And we show that indeed some polynomial dependency on k is necessary by showing a lower bound of square root k that also apply for the approximate DP case. Next, for the time window setting, we give an algorithm that has an error k times log cube t and a lower bound of root k plus log t. For the item level setting, interestingly, the Bolot et al.'s algorithm translates naturally here with exactly the same error. However, the nature of the problem changed substantially for the fixed window and time window setting. In particular, for the fixed window setting, we give an upper bound of k times t over w. Note here that the dependency on t is now polynomial, whereas before there was no dependency on t at all. And we also show that this is necessary by showing a lower bound of t over w plus square root k. Similarly, for the time window setting, before we have an error that depends only on log cube of t, but now we have an upper bound that is roughly t, and we also show a lower bound of roughly t as well, which shows that the problem becomes much harder here in the item level setting. So those are roughly the high level overview of our result. We'll next move on to how we prove these results. And for this, we will just focus mainly on the event level setting. And not only that, to make it even simpler, we will focus on only k equals to 1 case, or the count distinct problem. So our technical contributions here are that we show that these cumulative queries, fixed window queries, and time window queries are equivalent to different versions of the range query problem, which we'll discuss next. Once we show this, we can use known upper and lower bounds from the literature on differentially private range queries to get our desired results. In particular, for cumulative setting, we view the Bolot et al.'s algorithm as showing the equivalent between this setting and the range query problem on a domain of size t. For fixed window, we give a new reduction that shows the equivalent to the setting where the domain has size w. And finally, for time window, we show that it is equivalent to a two-dimensional version of the range query problem. Today, I will focus only on the first two results, which are based on the one-dimensional range query problem. So with that in mind, let us recall the range query problem in one dimension. Here there is a domain size D, and the input y is a vector of length d, where each coordinate is an integer. A range query is a query of the form asking for the sum from ys to yf, where again s and f are the starting and finishing point. Here we want differential privacy, and the differential privacy is under the neighboring notion, where y and y prime are neighbors if they differ on a single coordinate by a value of 1. For this problem, there are several known mechanisms. The most well-known one is perhaps the binary tree mechanism. The binary tree mechanism works as follows. As its name suggests, we build a binary tree on the d coordinates. We then fill in the value of each node by the sum of all the leaves that are below it. Now, this wouldn't be DP yet because we compute the values deterministically from the input. So we have to add some Laplace noise to each node to make it differentially private. If we scale the Laplace noise appropriately, then we can get the epsilon dp as we desire. So after adding noise and computing this differentially private data structure, how do we answer a range query? We answer it by summing up the appropriate nodes. In particular, we try to sum up as few nodes as possible. For example, if the range query is asking for the sum of y1 to y7, then we can take only the 3 nodes here and get the answer. The point here is that we only have to sum up at most log d of the nodes to get our result. So we are only adding up log d of the noise terms. Furthermore, each leaf affects only at most log d nodes in the tree. So the scale of the Laplace noise that we need to add is at most log d. Combining these two facts, we can conclude that the error here is at most log d to the 1.5 over epsilon. Okay, so that's the range query problem and the known algorithm here. Let us get back to our CalDistinct problem. We will now show the reduction from CalDistinct to range query, and we'll start with the cumulative setting. And recall again that this is the algorithm of Bolot et al., but we are writing it in this reduction form. So what do we want? We want to reduce CalDistinct to range query. So we start with the x1 to xn, which are the input to CalDistinct, and we want to compute and output y to range query. What are the properties that we need for this reduction to be valid? So we need two properties. First is the correctness. We want to be able to answer each cumulative CalDistinct on the x input using some range query on y. Furthermore, we also need this neighbor preserving property for differential privacy. This means that if x and x prime are neighbors in x and we feed it through this reduction, we want the resulting y and y prime to also be neighbors. And we can also relax this a little bit to allow y and y prime to be a constant distance neighbor. This only blow up the epsilon parameter by a constant, and so the error is still the same asymptotically. Okay, so with this goal in mind, let us try to do this reduction. So perhaps the simplest attempt here is to let y to be the sum of x1 to xn. So we just copy the x1 to xn over and sum them up and get y. So this doesn't work, and some of you might have already noticed it. And this is because there is a double counting problem. For example, let's say we want a cumulative query from 1 to 3. Then here, if we try to use the range query from 1 to 3 to answer this cumulative query, then we would be double counting this n element since it appears in both the second and the third time step. Whereas in CalDistinct, we want to count it only once. So how do we solve this problem? Instead of copying each xi over, we create a vector vi where the jth coordinate of vi is 1, even only if the time step j is the first time step that item I occurs. For example, here item 1 and item n occur for the first time in time step 2, and this is the reason why vi and vn have their second coordinate being 1 and the remaining coordinates being 0. And the y is defined again as the sum of the vi's. Now the correctness is not hard to see because we are now counting each element only once instead of double counting as before. In terms of the neighboring relationship, if we have xi and xi prime being neighbor, notice that the vi has at most one coordinate being 1. So changing from xi to xi prime will affect y in at most 2 coordinates. So y and y prime will remain a constant distant neighbors. So this is also fine. So this concludes the high-level overview of the reduction from Bolot et al. And we note here that this is a reduction in one direction from CalDistinct to range query, which gives an algorithm for CalDistinct. In the paper, we also show that there are reverse direction reductions as well from range queries to CalDistinct, but we will not be discussing it in this talk. Okay, so that's the cumulative CalDistinct problem. Let us now go back here and talk about the next setting, the fixed window setting. And this is a new reduction that we give here. As I said earlier, we are giving a reduction from this setting to range query on domain size W, where W is the window size. But for simplicity here, I will present the reduction where the domain size is T instead, which is a weaker reduction. There is a simple trick that can reduce the domain size from T to W, but I will not be presenting it here. Okay, so let's focus at this reduction from fixed window query to range query on domain size T. Again, the goals are pretty similar to before. We want the neighbor preserving relationship to get DP, and we want the correctness, where now the correctness means that for each fixed window count distinct query on X, we should be able to answer it using a range query on Y. So how do we do this? So the reduction works as follows. Again, we'll create vector vi for each xi. Roughly speaking, we want the vector vi to encode the difference between consecutive fixed window count distinct, but on only the xi element alone. What this means more formally is that the j coordinate of vi is equals to whether I occurs in the window from j to j plus w minus 1 minus whether I occurs in time j minus 1 to j plus w minus 2, or in other words, the difference between the answer in the current window and the previous window. Just to give you a more concrete example, let's consider w equals to 2 here, and let's consider item 1. To fill in the first coordinate of v1, we take a look at whether this item 1 occurs in the current window, and the answer is yes, it does. It occurs in the second time step. And then we subtract from it whether this item 1 occurs in the previous time window, and in this case, it doesn't occur in the previous time window. So v1 would be equals to plus 1. Next, we move on to the second coordinate of v1. And in this case, we would look at these two times windows. And since the item 1 occur in both time windows, the answer for this coordinate would be 0. Next, again, we move on to the third coordinate of v1. And now we look at these two windows. In the second window, the element doesn't occur, whereas in the previous time window, the element occurs. So here we are putting in minus 1. And we continue doing this for the rest of the VIs. Now, once we have constructed this structure, when we want to output a fixed window query from j to j plus w minus 1, we simply ask for a range query from 1 to j on y. And it is not hard to see that since we set each vi to be subtraction of the answer of consecutive queries, all the middle terms cancel out, and we are left indeed with the fixed window query answer for j to j plus w minus 1 when we ask for range query on y from 1 to j. So the correctness holds. For the neighbor preserving relationship, we will not show the full proof here. But the rough idea is that if we make a single event level change, then it will only affect the plus 1 and minus 1 in vi, that is immediately before and after it, and it will leave all the other coordinates alone. This means that it will affect only a constant number of vi's, which in turn means that it only affects a constant number of y by a constant amount. So we satisfy the neighbor preserving relationship as well. So that's a rough sketch for this reduction from fixed window count distinct to one-dimensional range query, which give us the first new algorithm in our paper. All right, so that's all the time that I have to discuss the technical contributions of our paper. So let me quickly conclude here. In the paper, we consider many different settings of count distinct and k occurring items in time windows. And the different settings include different neighboring relationships such as item level DP and event level DP. We consider the three different query families, including the cumulative time window and fixed window. Today, we only present the result about PLDP, but in the paper, we also consider the approximate DP case where delta is greater than 0 as well. We also consider the difference between bundle and singleton setting. The one I presented today is the bundle setting. In the paper, we also consider this singleton setting, which means that in each time step, at most one element is contributed across all the items. All the bounds that we derive in our paper are tied to within a polylogarithmic factor in the time horizon and polynomial in k factors. In some cases, these polynomial in k factors are not tied, and in all cases, we only get additive factors in the lower bound, whereas in the upper bound, they are usually multiplicative. So it remains an interesting question to close this gap. Another interesting aspect of the problem, which we haven't discussed today, is with regards to the streaming setting. In the streaming setting, we have to answer all the queries that we can answer immediately after we receive the input for time step j. It turns out that most of the range query algorithms, including the binary tree mechanism that we discussed earlier, already works in the streaming setting. So our algorithm, which proceeds by reduction to range queries, also work in this streaming setting as well. But the downside here is that we require memory that is linear in the number of items. There have been several previous works that try to get this memory reduced, and it remains an interesting question to get the type, privacy, utility, and memory trade-off for this setting. And with that, thank you all very much for your attention. Thank you.